Assalamualaikum. Welcome to the lecture number 43 for this course. In this lecture we are discussing chapter 8, principal stresses are under given loading. Previously we discussed principal stresses in a beam. Now in this lecture we will discuss design of transmission shaft, and for that we have to consider principal stresses. This you already have discussed in detail for the course of design of machine element. Course, but over here we will discuss again briefly the stresses on a transmission shaft and what will be the design criteria for that. Now let's see. Transmission shaft are used to transfer power from shaft by gear or maybe sprocket or maybe pulley, belt or pulley. So the shaft, if you draw the shaft, if you look at the shaft with the gear, so we have a gear, we have a shaft, so gear we have a transverse load acting on that. Now if we transfer this load at the centroid of the section, so we have a transverse load 1P1, and that is also cause torque T1, right? So if I take a section at the centroid and transfer force movement system over there, so we have shear transverse load P1 and we have torque T. And if I draw free body diagram for this whole beam, it will be, we have a reaction at A and B. Those are where we have bearings, and the beam loading is shown like this. Okay, so direction of P depending on where the other gear is meeting this gear. Okay, so but we have a transverse load as well as we have a torque. Now this transverse load will produce normal stress, okay, and that will be large as compared to the shear stress causing by this load P1. Okay, now we will we will ignore the shear stress due to transverse load. Means that if you're considering, we will only consider normal stress due to transverse load, because the contribution is large as compared to the shearing stress due to transverse load is small, and the contribution will be very small. So torque due to transverse load we will not consider. However, the shear stress due to torque T1, if we consider this shaft, T1, T2, T3 we have to consider. So we will, for the transmission shaft, we are considering normal stress due to transverse load, and we will consider shear stress due to torque. Okay, now on the shear stress we can calculate, we discussed in chapter 3, and torque and the bending stress or normal stress we consider, which we studied in chapter 4 and chapter 5 as well, how to find the bending stress due to transverse load we discussed in chapter 5, and we will find the normal stress due to transverse load. Okay, now if you look at the shaft and if you're looking at the cross section, so we have a torque and the transverse load can be causing bending moment. So transverse load can be in the direction of Z or Y axis or maybe some angle. So the component will be causing MZ and MY, whereas this is a circular cross section. So only we can take a resultant moment will be suffice, because it's is a symmetric about any plane passing through the centroid of the section. So maximum bending moment we can write sigma m will be mc over I, m will be my square plus mg square, considering this is my z-axis and y-axis, and along that is my x-axis. And the shear stress will be Tc by J. Now, the shaft can be hollow or shaft can be a solid cross section. Okay, now if I want to write, taking this is my x-axis and the other one is my y-axis, so I can write sigma x can be sigma m and tau xy will be tau m. Right? Now, if I want to find the principal stresses, so sigma max or minimum, those are my principal stresses. I can write sigma average plus radius, whereas sigma average is, in this case, it will be sigma x by 2, plus minus, and the radius will become sigma x by 2 because the y term is 0, and plus tau xy square because sigma y in this case is 0. Now, if you look at the loading condition, so sigma x will become sigma m by 2 plus minus under root sigma m by 2 square plus tau m by 2, sorry, not tau m by 2, that is simply tau m square. Now, if we solve this, so sigma max is tensile and sigma minimum will be compressive in nature, whereas the third principal stress will be 0 because it's a case of plane stress on the surface. Now, the maximum shear stress in this case will be equal to radius of the Mohr circle. So if I draw Mohr circle, so sigma A, so that will become my sigma max value. The point B is my minimum, sigma minimum, and the third principal stress is obviously 0, the plane stress case. So there will be a one circle over here, and the other circle will be between 0 and A. Whereas the maximum shear stress in this case is in plane shear stress. So basically this tau max is in plane for the transmission shaft. So why are we considering this maximum shear stress? Because most of the transmission shaft, they are made up of ductile material. So ductile material, their criteria for failure is a shear, and there is another criteria, so we will discuss, we are not discussing in this course, but usually tau maximum shear stress we are considering for the ductile material. So putting the value, so that is equal to the radius, so sigma m by 2 plus tau m, sigma m by 2 square plus tau m square, and if you put the value of sigma m and sigma sigma m and tau m, and we also know that J is equal to 2 times I, and we simplify it, so it will become tau max C by J under root m square by T tau square. Now if we know the material, we can find the cross section with the loading condition, or we can find the maximum shear stress and we compare how much factor of safety is there. So if the material is brittle, in that case we will considering sigma max. So that will be the criteria for the brittle material, because the brittle material, they are weak in the normal, under the normal stress condition. Okay. Now this is the maximum shear stress when you're designing the transmission shaft. Okay, and the shaft section you can find that will be equal to J by C minimum. Obviously you take the minimum. You have to find the optimal value to reduce the weight under root m square plus t square max divided by tau L. So you have to find where you have maximum combination of, at which location you have maximum combination of moment and torque. Okay, In some cases, the moment will be much more larger value than the torque, but the resultant will be small as compared to the other section. Oh, we will see. We will see a problem, and we will find out what this value of max is mean over here. Okay, and tau allowable is how much allowable shearing stress is there depending on the material. Okay, let's see a sample problem. It will clear. So a shaft rotates at 480 RPM. So this shaft that rotates because the dimension is given for this one. So we will consider this shaft AB. So that rotates 480 RPM and transmit 30 kilowatt from the motor to gear G and H. So from motor we are transforming the 20 kilowatt 30 kilowatt, and at G we are transferring 20 kilowatt, and at H we are transferring at H 10 kilowatt. And the dimensions are the length is given, the radius of the gear RC, RD and RE is given, and we have to find, knowing that sigma allowable, that is 50 megapascal, determine the smallest permissible diameter of the shaft. So how much smallest diameter we can select or find for this problem. Okay, now how we will solve this problem. So first, what we will do, sorry, this is not sigma allowable, that will be tau allowable. This will be tau allowable, not sigma allowable, because we are talking about maximum shear stress. Tau allowable. Okay, now what we will do, first we will find what will be the transverse force and what will be the torque acting at C, D and E. And then we will draw bending moment diagram as well as torque diagram, and we will find the location at which this value is maximum, m square plus t square under root, where it will be the maximum value. So we have to find the maximum, and based on that we will calculate the using the formula that was J by C and m square plus t square under root max divided by tau allowable, right? Okay. First, we will determine the gear torques and corresponding tangential forces, find reaction at A and B because we are considering as a beam. So we will find the critical shaft section for the torque and bending moment diagram, and this value basically. Then calculate minimum allowable shaft. Okay, now let's see. First we will find what will be the torque at different location, E, D and E. C, D and E, and also the forces, because we have to calculate the transverse load as well as the torque on that shaft AB. And so we know the value. So T power, we know 30 kilowatt divided 2 pi F. So we convert this 4800 RPM to frequency, revolution per second. So that will become 8 Hertz. So 8 revolution per second. So P divided by 2 pi F, we get the torque, and force we will find TE divided by radius. Similarly TC and TT. And the force will be what? It will become FC will be equal to TC divided by radius of gauge C, and force at D will be torque at D divided by radius at D. Okay, now we know the reaction forces as well as the torque. So we will find what will the reaction at A and B, draw the free body diagram. Since the rotation is allowed, so there will be no reaction torque at A and B, only there will be reaction force. So AY is 0.932 kilonewton, AZ is 6.22 kilonewton, BY at 2.8 kilonewton, and BZ is 2.9 kilonewton. Okay, now we will find what will be the bending moment and the shear force bending moment and torque diagram. Okay, now if you look at, we know the reaction Z and Y forces, we know the torque, and we have to find m square plus t square max. How we will find? So first what we will do, draw bending moment diagram with respect to z axis. Okay, so mg, so if we take a section between C and D, we take a section A and C, C and D, D and E, and we draw bending moment diagram only considering force acting along z axis. Sorry, force acting along y axis, and that will be bending about z axis, right? So this is the bending moment diagram with respect to z axis, and similarly we draw a bending moment diagram with respect to y axis and considering the force acting along z axis. Okay, now, and the torque diagram will be simply from A to C, that will be 0 torque. From C to D we cut it and we draw free body diagram for the torque, and we find the torque that we will doing in static as well as chapter 3, and these are the torque on different segments. Now we have to find the maximum value of the load. Okay, so where we have maximum value. Now over here it's written, it's shown directly, but if you consider, so if you take 186 and this is 100.1244 Newton meter, so the resultant will be, so if I want to calculate at C, what is the value? So it will be 186 square plus 1244 square under root. That is for the bending moment, right? So over here it will become, m will become 1257.8, but what is the value of torque? The value of torque is 398, right? But if we calculate this value over here, so this will become, if I want to calculate at C, I'm interested to calculate at C, that is m plus t, m square plus t square under root over here, so that will become 157.8 1257.8 square plus 398 square. So this will become 131.9, 131.9.2 Newton meter, which is less than this value, that is we are considering at D. So critical value is at D. If you can also check at E. So what will be the value at E? Please do this. Calculate the value of E, and you will find the critical value of this m square plus t square, that is at location D. Okay. For C I have calculated, so you can try for the E as well. Now this is my max value. Now based on that, I have to calculate, find the minimum allowable shaft diameter. So J by C will be m square plus t square divided by tau allowable. So tau allowable is 50 megapascal. We already calculated that is 1357. Put the value. So J by C ratio is 227.14 10 to the power minus 6 meter cube. We know that J is J by C. J value, we know that J is equal to pi by 2C4. Putting the value, so they will become pi C cube by 2. So solve it. So the radius is 25.82 millimeter. Sorry, 85 meter. So this should be millimeter, not meter. So this should be millimeter. So diameter, we can say 51.7 millimeter or 52 millimeter diameter. So this shaft, 52 millimeter diameter was suffice. Okay, now let's see another problem. A solid shaft AB rotates 600 RPM, transfer 80 kilowatt from motor M to machine tool connected at F. So there is a machine tool connected at F, and so this motor is transferring RPM, 600 RPM, and transmitting 80 kilowatt from motor M to machine to connected at gear F. Right? Means over here 80 kilowatt transferring, and also over here 80 kilowatt transferring from D to F. Knowing that tau allowable is 60 megapascal, determine the smallest permissible diameter of shaft AB. So we are interested in shaft AB. Okay, so we are not how much diameter is required for shaft AB. We will find what will be the reaction acting on that shaft AB. Okay, now first what we will do, we will find the torque. So we know that torque is equal to power divided by 2 pi F, and power we know that 80 kilowatt divided by 2 pi. Now RPM is 6000 RPM, sorry 600 RPM divided by 60, 10 hertz. So the torque is transferring is 1273.2 Newton meter. So this much torque is from transforming from the gear E to C, and the same torque is transferring from D to F. Okay, now if let's see, so at gear C, what will be the force? So force at C, so TC will be equal to TD, and that will be equal to 1273.2 Newton meter. Otherwise the direction will be different because it must be under static equilibrium. So force at C will be equal to TC divided by radius at C. So TC is 1273.2 divided by radius. Radius is 0.08 at C given. So how much force is 15.913 kilonewton. And similarly, FD will be equal to TD divided by radius of gear D, 1273.2 divided by, now radius is 60 millimeter, 0.06 meter, and this will become 21.221. Sorry. That will become 21.221 kilonewton. Now, if I draw, let's suppose, if I take this is my, let's take, this is my z-axis. Sorry, y-axis. Let's take z-axis. And this is my y-axis. Now, if I draw a free body diagram, so this is my y-axis. So what we have reaction at A, AY. This is reaction at B, BY, and there will be a force acting at C, and that force, let me take downward direction, FC. Now if I take, this is my z-axis. Now if I draw like this, so we have reaction at AZ, BZ, and we have at D, so this force at C, and at D we have a force, and that is FT. Okay, so we have to draw bending moment diagram with respect to moment about Y and with respect to moment about Z, and the torque as well. So torque is simple. So throughout the section CD, the torque is same. That is 127. 1273.2 Newton meter. But we have to find at which location we have maximum bending moment. Now, if I draw bending, first we have to find the reaction AY, AZ, BY, and BZ. So you can know the forces, apply sum of considering both axis, both cases. So if you calculate, so AY, if you calculate, so AY will become, that will become, let me write, roughly around 7 by 10 FC, and AZ will be 3 by 10 FT, and BY 3 by 10 FC, and BZ will be 7 by 10 FD, sorry, yes, FD. Now, if you draw moment diagram, so if you draw bending moment diagram for this case, so that will be moment about z-axis, mz. For this case, it will be moment about y-axis. So if you draw a bending moment diagram, or if you want to find what will be the bending moment at different location at C and D, so at C, so let me put MCZ, So that will be equal to 1336.7 Newton meter, and bending moment at D, so let me put MDZ, that will be equal to 572.9 Newton meter. Similarly for the Y, MCY, considering over here, so the bending moment at C will be 1782.6 Newton meter, or MDY will be equal to 764 Newton meter. So for this case, so the top case, the bending moment, so let me change color. So the bending moment diagram will be something like this. C, it will be maximum, and D will be 0. For the bottom case, for this one, it will be like this. So this will be D, and this will be C, MZ, and this will be MY. So please do try, and you will find where you have maximum bending moment and maximum bending moment and different location MY and MC. Now we have MCZ, MCY. So what we will do, we will find the maximum moment using this at C, and we will consider torque as well. And for point D, the bending maximum moment will be resultant of this one and the torque. So let's see. So if I want to find what at C is, at C, the value of m square plus t square under root max. So that will be equal to what? That will be equal to at C, mcy square plus mcz square plus tau square, because this is the resultant for the moment, and whole under root. So putting the value, so we already calculated, so this value is 1997.9 Newton meter. Similarly at D, the same value, m plus tau square under root this value of max at D, so that will be mdy square plus mdz square plus t square under root. We already calculated those values, so that will become 2264.3 Newton meter. Now, if you look at the maximum value, it's at D, that is 2264.3 Newton meter. Now, for the smallest diameter, we know that tau allowable is given. Tau allowable, we know that that is equal to C by J under root m square plus t square, or that will be equal to J by C is equal to m square plus t square under root divided by tau allowable. So putting the value to 264.3 divided by allowable is 60 megapascal, 10 to power 6. So value of J by C, we also know that that is pi by C cube, and pi by 2 times C cube, and if you calculate this value, so this will become 37.738 10 to power minus 6 meter cube. So solving it, C will become 28.85 10 to power minus 3 meter, or 28.85 millimeter. So diameter will be 2 times C. So if you multiply 2 times, so that will become 57.7 millimeter diameter, or roughly around 58 millimeter diameter is sufficient or allowable for the shaft for the loading condition given in problem 8.23. Okay. Now, some such assignment problem from section 8.1 and 8.2. From section 8.1 and 8.2, that is beam design and also design of shaft. So these are some assignment problems. Please solve those problems, and you will it will be get much clearer. The concept will much clear to you. Okay, thank you very much, and see you inshallah next.